Today I will be talking about imaging analysis. Before I begin, don't forget to hit a like and subscribe and comment if you have any suggestions or questions. I will start off with a question. What are the different parts of an imaging system? If you've answered hardware and software, kudos to you. If not, please go back and watch my previous videos. In our previous videos, we have mainly focused on the hardware part. Today, we will be beginning on the software part, which includes imaging analysis. Let me select this highlighter. Okay, so imaging analysis involves manipulating the image data to determine exactly the information necessary to help solve a computer imaging problem. This can be different for different problems. For example, for fingerprint recognition, we will need to find the indents on our finger. For face recognition, we will need our face, and so on. Often, much of this information is not necessary to solve a specific computer imaging problem, which is exactly what I just said. So, a primary part of image analysis task is to determine exactly what information is necessary. Image analysis system can be broken down into three primary stages: pre-processing, data reduction, and feature analysis. Suppose if this is the input image will first undergo pre-processing, next it will undergo data reduction, and then it will undergo a feature analysis portion. We will look at each of these individually. For starters, pre-processing. It is used to remove noise. What is noise? Noise is unwanted information that can result from image acquisition process. This can be some background light noise and so on, and eliminate irrelevant, visually unnecessary information. Next, gray level or spatial quantization. It is reducing the number of bits per pixel in an image size. Unless the work you need needs extremely high, well-defined images, we can usually do with less bits per pixel. We can work with less bits per pixel. In this way, the processing is faster and so on. Finding the region of interest for further processing. We will look into what region of interest is later on in this video. This all falls under the step of pre-processing, this one. Now let's move to data reduction. Data reduction means reducing the data, either in spatial domain or transforming it to another domain called the frequency domain, and then extracting the features for analyzing process. Feature analysis. Once we have extracted the features from data reduction process, these features are examined and evaluated for the use in the application. After pre-processing, segmentation can be performed. If you remember, segmentation means taking out the part of the image that is actually required on the image in the spatial domain, or we can convert it to another domain, which is the frequency domain, using a mathematical transformation function. Once three of the steps are completed, images can be filtered, which reduces the data even more and allows us to extract the features that may be required for analyzing. Let us look at this image analysis system. First of all, we input the image. Next, we do the pre-processing. After pre-processing, we can transform it to another domain, which is the frequency domain, or we can segment it. Segmentation means bringing out the required part of the image. Both of them can be filtered. From here, we can extract the features, and from here, we can perform analysis on those features. Now, if you can see, this is pre-processing. Next part is data reduction, and then is feature analysis. So this dotted part is actually the data reduction process. Also, we can see that there is a feedback loop here. This continues until the process gives out satisfactory results. Now we will be talking more about pre-processing. The pre-processing algorithms are operators that are used to perform initial processing that makes the primary data reduction and analyzing task easier. So what are some of the pre-processing tasks? They are extracting region of interest, performing basic mathematical operation on images, simple enhancement of specific image features, color space transformation, and data reduction in both resolution and brightness. The pre-processing stage, requirements are typically obvious and simple, such as the removal of artifacts from images. This means removing unnecessary details from images, or elimination of image information that is not required for the application. For example, the whole hand picture is not needed in a fingerprint processing system. We only need the thumbprint and so on. Now, a term that we just looked at before, region of interest. To investigate more closely a specific area within the image, region of interest is used. To do this operation, the spatial coordinates of the image need to be modified, and these are categorized as image geometry operations. That is, from the entire image, we can select a portion of the image. That is the part of the image that we will work on. The image geometry transformation typically include crop, zoom, enlarge, shrink, translate, and rotate. Crop process is the selection of a portion of the image, a sub-image, and cutting it away from the rest of the image. Zoom is enlarging that cropped image. Enlarging is zooming the entire image. Shrinking is shrinking the entire image. That means making it smaller. Translate means moving it from one point to another, and rotate means rotating it simply. Image enlargement is useful in a variety of applications since it can show detailed objects. For example, some imaging applications require that two input image may be in tight geometrical alignment prior to their combination. This process is called registration. Improper alignment of images can produce distortion at object boundaries. Enlargement of images eases the task of manual alignment. I will draw and show an example of this. Suppose this is image 1, and suppose this is image 2. When we combine them, we have to combine them in such a way that these wedges align. If not, it can produce a distortion. It can produce a distortion at the object boundaries. If we enlarge this, we can do it manually, easily. Furthermore, enlargement may allow a visible recognition of image degradation, helping in the selection of restoration model. We will be talking about restoration models when we talk about image restoration. Now, how can we perform zoom? The zoom process can be done in numerous ways. We will be looking at two. One of them is the zero order hold, and the next one is first order hold. for zero order hold, we can see that the images are just duplicated. 8, 4, 8, 8, 4, 8, 8, 4, 8, 4, 8, 2, 4, 8, 2, 4, 8, 2, 8, 4, 8, 8, 4, 8, 8, 4, 8. What have we seen here? This means that the previous pixel values are repeated. This can cause a blocky effect, which we will see a bit later. The first order hold includes a bit of calculation. Suppose we want to select this row. We want to calculate this row. So for the first value, it will be 8 plus 4 divided by 2 is equal to 6, and is 4 plus 8 divided by 2 is equal to 6. Next is 8 plus 2 divided by 2, which is equal to 5. Okay, so what have we done here? We have taken this value 8 and the adjacent pixel value 4. 8 plus 4, we have taken the average, which is divided by 2, which is equal to 6. This 6 we have inserted it here. So for the next one, correspondingly we do the same, which is 4, then the adjacent pixel value is 8, we have taken the average, which is divided by 2, which is also 6, and we have inserted it here. Next we have done this 8, sorry, I made a mistake here, this is going to be plus 8 plus 2, divided by 2, which is the average, which gives 5. Can you tell me how we have gotten this value here? Leave it down in the comment section below. Okay, let me select my highlighter. So what have we learned here? We have learned that first order hold is the linear interpolation between the adjacent pixels 8 and 4, which are adjacent, and finding the average value between those two pixels and using that value between those two. I'm sure you understood with the example. Now we've learned two methods, which is the first one is zero order hold, the second one is first order hold. We will now be doing a comparison of the images resulting from the two methods. This one is using zero order hold, this one is using zero order hold, and this one is using first order hold. I'm not sure if it's showing up in the camera very well, but this one, if you can see, is causing a blocky effect. However, this one is more smoother. Why does this one cause a blocky effect and why doesn't this one cause a blocky effect? If you know the answer, leave it down in the comment section below. Now, as we have said, preprocessing can include a lot of operations. Some of them are arithmetic and logic operations. Arithmetic and logic operations are often applied in preprocessing steps in image analysis in order to combine images in various ways. So what is the main point of arithmetic or logic operations? They are mainly used to combine images in various ways. Sorry for that. Okay, addition, subtraction, division, multiplication are arithmetic operations, and or not are logical operations. All of these require two images because we're combining on two images, except for not, which can be done on one image and can be done on pixel by pixel basis. I will give a better explanation of this when we come to this. For example, suppose I1 is image 1 and I2 is image 2. Now we create I3, which is image 3, which is the combined image, which is just simply normal adding, which is pixel by pixel adding. 3 plus 6, 3 plus 6, 4 plus 6, 4 plus 6, 7 plus 6, 7 plus 6, and so on, and we get the corresponding I3 image here. Now, why do we need this? Addition is used to combine the information in two images. It is also used in image morphing. Now, what is image morphing? It can be shown better with an example. For example, this is a picture of a boy. This is a picture of a bear. If we want to morph these two images, that means if we want to morph this boy into a bear, this is how we do it. This is the resulting combination. This is the resulting combination of adding two images. Subtraction of two images is often used to detect motion. Consider a case where nothing has changed in a scene. The images resulting from subtraction of two sequential images is filled with zeros, a black image. Okay, let me try and show this with an example. I added in the examples of camera. So suppose we take a snapshot of a scene. This is the first image that we get, and we take a snapshot at the second instance where nothing has changed. What do we get? If we subtract 10 minus 10, we get 0, 1 minus 1, we get 0, 1 minus 1, we again get 0, and so on. So what we get is an image filled with zeros, which means a black image. Now, if something has moved in the scene, subtraction will produce a non-zero result at the location of the movement, enabling detection of both motion and the direction of motion. Okay, so suppose this is scene 1. We took a snapshot of a scene and we got these set of pixel values. On the next instance, we took another snapshot where we got these values. As we can see here in this part, it's 9 and here it's 7. 1 minus 1 will give 0. For the rest of all, it will give 0. For 9 minus 7, it will give 2. It means at this instance or at this location, there was a motion, and we can determine the direction because 9 minus 7 is a positive value, which means it's in the positive direction. If it was, suppose if the value here was 7 and this was 9, it would give a minus value, which would mean that it's in the opposite direction. It will become a bit more clear when I show an image example. But for now, let's move on to multiplication and division. Multiplication and division are used to adjust the brightness of an image. This is also done on pixel by pixel basis, which means we take one pixel and we do it just like how we have done for addition and subtraction. And the options are to multiply or divide an image by a constant value or by another image. Now, if we multiply the pixel values with a value greater than 1, it will brighten the image. Or if we divide it by a value less than 1, it will brighten the image. But if we divide by a factor greater than 1, it will darken the image, or multiply a factor with less than 1, it will darken the image. I will show it only with one pixel value instead of multiple ones. Suppose this is our pixel value 2 and our constant factor is 0.5. We will get 1. We can see that multiplying it with 0.5 has decreased the value, which means it will darken the image. Now, if we do 2 divided by 0.5, we get 4. This means the value has increased, which means that the image will brighten. Now, suppose we do 2 into 2, we will get 4. So we will get a brighter image because the previous pixel value was 2 and now it's 4. Now let us do it for division. sorry, let me go back here because I'm running out of space. I'll just show it here. 2 divided by 2 is equal to 1. 2 is our pixel value, and this 2 is our constant value with which we are multiplying or dividing, and we get 1. Our previous pixel value was 2, and now we have 1, which means it's a lesser value, which means the image will darken. Now let us look at some examples. Wait, let me select the highlighter. Okay. Suppose this is scene 1 or image 1, and this is scene 2. And once we have subtracted the image, we get this value. We can see that the car has moved from this point to this point. The car has moved from this point to this point. Everything else in the scene that is similar is represented by black. Now let us look at a multiplication division example. This is the original image, and this image we have divided by a value less than 1 to brighten it up, and here we have divided by a value greater than 1 to darken it. How would we have done it if we have multiplied it? Leave it in the comment section below. Now let us come to the logical operations or operators and, or not. The logical operations and or are used to combine information in two images. They can be done for special effects, but they are done to perform a masking operation. We will look into what a masking operation is just a few minutes later. And or can also be used as a simple method to extract ROI. Now let us look at an example. For example, a white mask ANDed with an image will allow only the portion of the image coincident with the mask to appear in the output image with the background turned black, and a black mask ORed with an image will allow only the part of the image corresponding to the black mask to appear in the output image but will turn rest of the image white. This process is called image masking. First of all, to understand how this works, let us review how and or works. Okay, so this is OR. I have prepared this off camera, but as you can see, I've forgotten to write the OR here. Okay, so 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. This is just the basics. This is just for a review purpose. Now let us look at this with an example. This is an image. Suppose we only want to get this cat on the right. Now suppose the values of this cat here, suppose this is the value, okay. Now suppose the value of this one, whatever the values of this one here is. Now this is the mask that we have created. Black background, and the part of the cat that we want. We only want the cat on the right. We have made this mask, or we have made this outline as all ones, which means all white. Now if I do this and this, what do we know? When we do and 0 and 1 we have 0, 1 and 1 we have 1, which means when we do and something and 1 we get whatever was remaining. Sorry, this one. Let me minimize this. So this and 1, which means this and 1 of this part, will give us this. Because the rest of everything was 0, everything else will turn black. Why does everything turn black? Let us look here. Something and 0 gives 0. Something and 0 gives 0. So everything else and black, which means 0, will give black. Now let us look at how to do image masking and region extraction using OR. The one that we previously did was using AND. Now we are going to do it using OR. Suppose we want to extract the same thing. We want to extract this cat. Now we want to extract this cat. The image mask for this, the mask for this is this one, white background and black image. The black part is the portion that we want to extract from our image. Why does this work? Now let us refer back to our truth table. 0 or 0 is 0, 1 or 0 is 1, which means something or 0 remains the same thing as previously. So 0 or 0 is 0, which means 0 remained as 0. 1 or 0 is 1, which means 1 remained the same thing after ORing it, after performing an OR operation on it. Suppose if this is our cat which we want to extract, so this cat, the pixel values here ORed with the values of 0 here will remain this cat. This cat will remain. The background here was white. Now let us look at this. 0 or 1 is 1, 1 or 1 is 1, which means anything ORed with 1 becomes 1. So 0 or 1 is 1, 1 or 1 is also 1. So everything else in the background, everything else in the background is white. So everything else here ORed with 1 will also give 1, which means a white background. I hope you have understood this, because this is a very important aspect of digital image processing. It's a very simple process but very important. Now the NOT operation creates a negative value of the original image by inverting each bit within the pixel. If the pixel was something like this, it will then become something like this, inverting the images. For example, which is what we did here, this is the AND mask. Once we invert the AND mask, we get the OR mask. So someone comment down below how the whole process works. This was a rather long video and we looked at a lot of interesting things. We looked at image analysis system, pre-processing, how we get region of interest, how we zoom them, arithmetic operations and logical operations, where we use them, why we use them, and how we use them. I hope this has helped you, and if you have any confusion, leave it in the comment section below. Thank you.